This video is going to take very little time, but I am glad that you're looking at it because it can have a lot of benefit to you as you work through Chapter 5. This video is called Introduction to Entropy. The chances are, I'd say very good, that you may never have even heard the word entropy before you step foot in this class. That is possible. As I think back about my own situation, I had never heard that word until I got into Chapter 5, or the equivalent of it, when I was a student in thermodynamics class. And so the question is, what is entropy and why is entropy? And so a reason, before we start defining it, is that you probably have observed in your life a couple of types of processes or situations where you're going from order to disorder, order to disorder. The classic example is a set of rows and columns of marbles, and you pick them up and you throw them up in the air. That's going to be from an ordered set to a disordered set. And then, gosh, you can think back as a child and being assigned certain tasks to go from disorder to order. In other words, put your room into order. Your room is disorderly. Put your room into order. I was assigned that both at school and at home. And so I hope that gives you an idea, at least some general working concepts of the idea between disorder and order. And so now back to thermo class. So recognize that entropy is a property. And in this class, I put a pretty big text box up there. It's either going to be capital S, that's the extensive version of the property entropy, or little s, the intensive version of entropy, little s. Okay, so how can I get you more comfortable with thinking about this stuff? Properties you already know, properties, pressure. Here's a visualization, force over area. Volume and specific volume, size, the volume of something. You got to feel for it. Temperature, you got to feel for the property temperature. It's a hot or cold. Internal energy, you have a pretty good idea of that. It's an energy content term. And then enthalpy, it's also an energy content term, but we remember that it had something to do with flow work, and that's all you need to remember. But you've got a feel for those properties already. Now in Chapter 5, we've got a new property called entropy, capital S and little s. And here's your visualization. So you got the idea of the visualization over here on stuff you already know? All right, new visualization, entropy. The visualization of entropy is a measure of disorder. And I got to tell you that it took me a number of different courses in thermo to get to this. And so you can maybe just go with me on this. This is a suggestion. My suggestion is to you to visualize entropy as a measure of disorder. So for example, when S is a low number, when S is a small value, then it's more ordered. Things are more orderly within, let's say, a closed system, more orderly. And I like the visualization of the marbles, okay? S would be a low number on the left-hand side of the sketch. But if you took those marbles and threw them up in the air, they landed just anywhere, that would be a measure of disorder, and the property entropy S would be a larger value than what you over here. Large value of S, smaller value of S. And we're just going to leave it at that. So you're in Chapter 6, you're going to understand, you're going to learn how to quantify that, put a number and a unit associated with S. But for right now, S is a property and it's a measure of disorder. The more the disorder, the bigger the value. Now, how is entropy defined in thermodynamics? And so I've taken a clip out of, this is the traditional and correct definition from your textbook. So entropy change, entropy change, capital S2 minus capital S1, a change in the measure of disorder. Entropy change is defined in terms of a differential equation. So this is 6.2 out of your book. All right. So what does it say? Left-hand side, the change in entropy for a system going from state 1 to state 2. So S is a property. So we've got S final entropy minus initial entropy equals. Right-hand side, it's an integral. It's an integral of del Q, incremental change in heat, divided by the temperature at which the heat is being transferred as we go through process 1 to 2. And you can only do that integral along a reversible path. A reversible path. We just covered that. You got internally reversible path. Okay, so this is worth going to your book. It's worth sort of studying on this slide because I've tried to say in words what these text boxes say. And then moving down, do you see what we do is we turn this integral expression into a differential equation expression by taking the incremental change. That's the way we get rid of this integral sign. And so it says the incremental heat, so ds, the incremental change in entropy, it's a property, incremental change equals the right-hand side, del Q over T. It's each little incremental piece of heat transfer. It's being transferred at a certain temperature, depending on the path, the internally reversible path you're taking along a tiny little incremental process. In other words, not state 2 and not state 1, an incremental process in between 2 and 1. So this is the technical definition of incremental change in entropy. And so you're looking ahead and you're saying, oh, shoot, this differential equation stuff, I can't put numbers to that. I'm an engineer. I want to get numbers to get a result in. Don't worry, we're going to get there, but this is the definition of the change in entropy, equation 6.2a, and the incremental change in entropy, equation 6.2b. So let's just go with that. Let's go with that and see where we go in the chapter. Well, we've got to visualize heat transfer for a reversible process. And so let's see, we've got ds is del Q over T. That was our definition. Okay, so let's just go with that. Let's multiply both sides of this definition relationship by T. And so left-hand side, we're going to get TDS is equal to del Q reversible. Right-hand side, let's not dissect that just yet. Let's just say we've got to go along a reversible process path, like a quasi-equilibrium process where we can define the path with an equation. That's the right-hand side. Well, now if we integrate both sides from state 1 to state 2, the integral of TDS is the integral of del Q from 1 to 2. Well, gosh, the integral of del Q across a process path is simply Qn from 1 to 2. So I've labeled the right-hand side, instead of this funky integral, I'm just calling it Qn. It's a number. It's kilojoules, Qn, in terms of kilojoules or BTUs. And so here's the point I want to make is the left-hand side, you can visualize this on a temperature entropy diagram. And this is the first time I've ever mentioned, at least on the videos, a TS diagram. Well, here it is. Temperature on the Y and entropy on the X. And so you see that you can visualize Qn as an integral of the process path on the TS diagram. That's like Y dx. See how Y dx. The integral of y dx is the area under the curve. And that's why this little short video is extraordinarily important, is that we're introducing the idea of a TS diagram. And what good does it do me? The good that it does you is that you can see with your eyes, if you go from state 1 to state 2 across a reversible process, quasi-equilibrium, then you can visualize the heat added. It's the area under the curve for a reversible process. Shaded area is the visualization of Qn for the reversible process 1 to 2. That's really important. And so you may be saying, well, that's obvious. I'm going to have to tell you that it was not obvious to me as an undergraduate student. So my professor really had to work. He had to work very hard for all of us in class. I wasn't just the only dum-dum in class. There were plenty of us together, but we really had to work hard to get an understanding of this, that the value of a temperature entropy diagram, it's not just an assignment, it's got value. And for a reversible process, we can visualize the heat transfer on the TS diagram for a reversible process. Well, that brings us to the end of this video. And there will be some homework problems that will help you. We're going to go on to talk about a little bit more. Let's take a recap of what we covered in this video. Entropy is a property. It's a measure of disorder. It's a property, just like you've mastered other properties. Now we're going to add one, entropy, S. Okay, it's a measure of disorder. The bigger the number, the bigger the entropy value, the more disordered it is. And then entropy change is defined. How do we define entropy? In this class, we define it beyond saying it's a measure of disorder. It's defined in terms of a differential equation across a reversible path. Entropy change is defined in terms of a differential equation across a reversible path. So that's it. Look, it's only 6 slides in this video, so that's a little different. But I wanted to take the time and devote one video to what is entropy in the first place, because you got to wrap your head around that entropy is a property before you move ahead and start understanding how to use it as a extraordinarily powerful problem-solving tool. So I can only encourage you to hang in there, keep up with the homework, and keep plugging away, because you will discover that the use of understanding the second law of thermodynamics, particularly as it relates to entropy, can be a tremendous problem-solving tool for you in the future as a practicing engineer.